So our last example in this section is a nice example with a rational function. Hugely important on this one that you know how to do this problem. This one does have a little more difficult factoring than I'd probably do on the test. It would probably be a simpler rational function, but certainly a rational function can and most likely will be on the test. So very important problem here. Again, it says find the intervals of increasing and decreasing in relative extrema of f of x equals x to the fourth plus 1 over x squared. So again, we're going to be doing the sign chart method for the first derivative. Where the derivative is positive, it's increasing. Where the derivative is negative, it's decreasing. Where it changes from increasing to decreasing, the first derivative test says it's a max. And where it changes from decreasing to increasing, the first derivative test says it's a minimum. So let's go ahead and get started. First thing we want to do is find those critical values. Okay, rational function, if you remember this, we have to use the quotient rule. Well, that's not entirely true on this problem if you don't want to use the quotient rule, because it is only a single term in the denominator, so you could set it equal to, or separate it and simplify. In fact, if that's what you saw, that's what I'm going to do, is look at it as, I'm going to look at this as x to the fourth over x squared plus 1 over x squared. When I do that, I would end up with x squared plus x to the negative 2. So that's actually what I'm going to take the derivative of, so I don't need to use the quotient rule on this one. Kind of cheating, definitely not what they do in the textbook, but hey, if it works, use it, I guess, right? Okay, so when I find the derivative, what's the derivative of x squared? The derivative of x squared is 2x. What's the derivative of x to the negative 2? Would be minus 2x to the negative 3, or that would be negative 2 over x cubed. The only thing is, if I do it this way, I do need to get a common denominator. So I'm going to multiply the first term by x cubed over x cubed. And when I do that, I'm going to end up with 2x to the fourth minus 2 all over x cubed. That is my first derivative. Okay, so to find those critical values, I need to find when is the first derivative equal to 0 and when is the first derivative undefined. That's how I find my critical values. So let's start with the first one. F prime of x, 2x to the fourth minus 2, when is a fraction equal to 0 is when the numerator, 2x to the fourth minus 2, is equal to 0. Well, we have to be really, really careful on this one. First thing I'd do is divide everything by 2, and if I divide everything by 2, I'd have x to the fourth minus 1 equals 0. And when I do this, again, I still need to be careful, because what I'm going to be doing is taking a fourth root. And you're probably not used to taking it, well, it depends on how you do this, but you're probably not used to taking a fourth root. If I add 1 to both sides, I'd have x to the fourth equals 1, and if I take the fourth root of both sides, like the square root, I need to remember there's always a plus and minus. So this is going to give me x equals negative 1 and positive 1. The fourth root of 1 is negative 1 and positive 1. Okay? So those are my critical values where the derivative is equal to 0. Let's look when the derivative is undefined. Well, that would be when the denominator, which is x cubed, is equal to 0. Remember, a fraction is undefined when the denominator is equal to 0. Cube root both sides, and we simply get x equals 0. Notice if we go back into the original function, we got to be really careful. Is this function defined at that original point? Okay, at that point, and so let's look at it. Think about plugging negative 1 and 1 in. Negative 1 and 1 would work, but plugging in 0 does not work because it's division by 0. So this number right here, this x equals 0, is not a critical value. We still need to break, because it's not in the domain of the original function. It can't be a max or a min because the function doesn't exist at that point. So it's huge that you always think, does this function exist at that point? It can't be a maximum or a minimum if it doesn't. Okay, so the other two, though, are critical values because they are in the domain of my function. Either way, I need to break it up at all three of these points. So let's go to step 2. Again, step 2 is creating that number line. When we create that number line, we're going to go from negative infinity to infinity. We're going to plot the points negative 1, 0, and 1. We're going to think about our derivative, f prime of x. So our derivative at negative 1 was 0, and at 1 was 0. And this was undefined, and I'm also going to note right now that my original function at that point is undefined as well, because I do not want to make the conclusion that that point is a maximum or a minimum. Even if it goes from increasing to decreasing, that point does not exist and cannot be a maximum or a minimum. Okay, so let's continue on this one right here. What are our intervals? Our first interval would be negative infinity to negative 1. Second interval would be negative 1 to 0. Third interval would be 0 to 1. And our last interval would be 1 to infinity. So we know which intervals we have to test. Let's go ahead and make test points and complete the sign chart. The sign chart is completed with plugging numbers into the derivative from each one of these. So we're going to plug this into the derivative. The derivative was 2x to the fourth minus 2 all over x cubed. Again, we have to think about, is the value positive or negative? So we need a point from each interval. So negative infinity to negative 1, I'll choose the point, how about negative 10? From the point negative 1 to 0, how about negative 0.5? From the point 0 to 1, how about the value of 0.5? And then from the value 1 to infinity, how about the value 10? Okay, so let's think about this. Plugging in negative 10, what would happen? Negative 10 to the fourth would be hugely positive, so the numerator would be positive. The denominator would be negative 10 cubed, which would be negative. A positive over a negative is negative. Negative 0.5. Negative 0.5 to the fourth times 2 minus 2 would actually be a negative number. And then negative 0.5 cubed is also a negative number. A negative over a negative is positive. 0.5, again, 0.5 to the fourth times 2 minus 2 is a negative number. 0.5 cubed is positive this time. And a negative over a positive would be negative. 10, 2 times 10 to the fourth is a huge number, minus 2 would still be positive. And 10 cubed is positive, so we have a positive over positive, which is positive. I promise you, it does not need to alternate every single time. It doesn't go negative, positive, every single time. I can make it do whatever I want. So I can have it do negative, negative, positive, positive, whatever I want, I can have it do. Okay? So don't just get into a thought that it has to go from negative to positive. All right, so let's look at this. At negative 10, the derivative was negative, so that entire interval is negative. Negative 0.5, it was positive, so that entire interval, the derivative is positive. 0.5, it was negative, so that entire interval, it was negative. And 10, it was positive, so that entire interval, it has to be positive. Let's think about our original function f of x. Where the derivative is negative, the function is decreasing. Where the derivative is positive, that function is increasing. Negative, again, would be decreasing. Positive, again, would be increasing. So I already know my intervals of increasing and decreasing. Let's do those now. The intervals of increasing were, where the derivative was positive, was negative 1 to 0, and also 1 to infinity. The intervals of decreasing were negative infinity to negative 1, and 0 to 1. So now the question is, do we have any maxes or mins? And we need to be very, very careful here. At negative 1, we notice that it goes from decreasing to increasing, so it's a min. Likewise, at 1, it goes from decreasing to increasing, it's a min. But I want to point it out. This one, even though it looks like a max, this cannot be a max because it isn't in the domain. Now, how could have you gotten that to begin with if you didn't catch it at the beginning, if you didn't see that this is in the domain? Remember, the next part is to find the ordered pair of the maxes and the mins. In other words, you have to plug these values into the original function. And if you plug that value into the original function, you would have quickly seen that that is undefined at x equals 0. So let's go ahead and do that. We're looking at step 5. We're going to plug into the original function, f of x, any of our extrema. The ones that we know of are extrema. Again, here's the x value. We're plugging it into the original function. Again, let's zoom up and see what the original function was. It was x to the fourth plus 1 over x squared. X to the fourth plus 1 all over x squared. And the idea here is we need to plug in the critical values that we found, which were negative 1 and 1. Again, if you plugged in 0, you would quickly realize that it was undefined. So let's plug this in. Negative 1 to the 4th is 1, plus 1 is 2, all over negative 1 squared, which is 1, so that would give me a y value of 2. 1 to the 4th plus 1 is 2 over 1 squared, which is 1. 2 over 1 would also give me a y value of 2. I know at both of these points I have a min because it went from decreasing to increasing. So the first derivative test states those must be minimum. So my first maximum, let me go back. The maximum was none, and then the minimum were the points negative 1, 2, and 1, 2. 2 minimums on that problem. Hope that helps you out.